I also see cases where the idea of how we connect variables is left a bit vague. So, for example, X and S in the match model, they've got to be connected by something, right? I mean, the language of the problem said, same person. We can formalize this principle when we talk about our variable representing that person, kappa, in the following way. If we have a variable in a model structure that connects multiple observables, we cannot remove it from the information graph without changing the conditional independence of those variables, right? So going back to the picture that I just showed you a moment ago. So here we're talking about, for example, kappa. If I take this out of the picture, now I have X and S just going straight back to theta. And that's now a claim that X and S are conditionally independent given theta. And that's just not a true statement about the match model. The match model we said from the same person. That person is not, the state of that person is not represented just by theta. There's more connecting X and S than just theta under the match model, okay? So in general, if you're staring at a problem or an information graph and you're wondering, do I really need that variable? You can ask yourself the following very simple question. Does it connect multiple observables? If it does, then you can't get rid of it without changing the model structure, okay? So for example, I could stick all sorts of extra things on this edge to make up extra variables, right? And I'm saying under the principle that I just stated that I can get rid of those because all they do is they chain down to this one observable. They don't, removing them doesn't alter the connectivity of our observables. Okay? So one way of thinking about that is that, I could basically use the projection principle that we talked about in class to sum over all possible values of, let's say I had some variable epsilon or something hidden on this edge. Well, I sum over all possible values of epsilon and it vanishes from the picture, and now I have this edge going straight from kappa to x. Well, epsilon didn't connect to any other observables other than x, so it doesn't change the connectivity. If I had another observable that epsilon connected in to, sure, I mean, if I had a picture where I had, I'll just draw another, how about sticking to the IJK, I'll have an iota, and maybe, it connects to X and it also connects to Y. Okay, now I can't get rid of iota without altering the connectivity of my observables. Okay. So, just to probe a little bit more into that connectivity question, you can ask the question, for example, in the mismatch model, do we really need kappa and lambda? Okay? So, just to make the hopefully obvious point that I just made a moment ago about eliminating variables by summing over all possible values, we could eliminate kappa, right? Just mathematically, clearly, we could do this, and from this probability, we'd be able to reduce it to a likelihood that would just be probability of x conditioned directly on theta, okay? These variables don't actually connect to any other observable other than just one observable directly, right? So you could ask yourself, well, gee, maybe we don't really need kappa and lambda. Right? We just go straight from theta to x and straight from theta to s. Why not? Well, here's my answer, why not? The basic idea is each edge should be a likelihood model. One model. Or maybe a simpler, more concrete way of saying that, one peak. This is what probability of x given theta looks like. And here I just stuffed in some representative numbers like theta equal 0.5 and a standard deviation from my normal distribution of 4.1. You can see 3 peaks here. The height of these peaks are being determined by my theta value. As I change theta, the peaks are going to change in height, right? And then the width of these peaks is being determined by the standard deviation from my detector noise, basically for the readout of the fluorescence, right? So, just to state this in very intuitive terms, I would assert to you, this is not one model. This is 3 models. Because basically, what this represents, just to reduce it to simple terms, there's kappa equals 0, there's kappa equals 1, and there's kappa equal 2. Right? That's what's producing those 3 peaks. The height of those peaks is basically probability of kappa given theta. So the principle that I'm urging to you is one edge in your information graph should correspond to one likelihood model, which should be one peak for the likelihood of your observable. Okay? To further justify this, why should we follow this single peak rule? Basically, to my mind, this is safety for you or for whoever is trying to think about a model. Because this is what keeps us honest. I mean, if an edge in an information graph has to follow this rule, it basically means each edge is some kind of standard likelihood model that you understand. It's a binomial, or it's a normal, or some straightforward likelihood model like that that you understand. And actually, just by glancing at the information graph, therefore, you can understand what the model is. Because each one of those edges, you can understand what it is, you can see what all the edges, how they connect together, and you go, I understand this. By contrast, if on any given edge, I can stuff in there any darn thing I want, and actually as many things as I want, and make it as complicated as I want, you look at the information graph structure, and you don't even know, oh, that one edge there, he hid like 19 things inside there. What's the model? You don't know. You don't even know you don't know, because you don't know that I stuffed 19 things in there. Okay? So what that really means is if you don't follow this rule, then the meaning of the model, quote unquote, is no longer visible in the information graph, right? Because stuff could be hidden inside a single edge, swept under the rug somewhere in there. The obvious point is the person that this helps is you, the person who's trying to think about models and make models using this kind of graphical picture. Just to be very concrete about this, I mean, how likely are you to figure out this correct, properly mixed likelihood if you haven't even realized that there's a hidden variable, kappa, that plays a role in producing this likelihood? I mean, why are there 3 peaks there? Because kappa has 3 possible values. If you didn't even realize kappa is important for this problem, how are you going to come up with those 3-peak model? I mean, and get the right weighting and all that stuff, right? So, follow the single peak rule. Questions about what I mean here or what I'm saying? Sure. The y-axis is probability density. This is a PDF for a continuous variable x representing our fluorescence. And that's x along the x-axis, and that's p of x along the y-axis. Other questions? Right, so when we have a binomial with a 50% probability, it's like there's two ways of getting one head and one tails, and only one way of getting two heads and only one way of getting two tails. So you get a 1 to 2 to 1. Other questions?
So if to remove a variable, we make sure it doesn't lose the connectivity and also the edge would still be connected by one module.
Yeah. Oh, sorry. Go ahead. Okay, so you just asked a really, really important question that is important for understanding the difference between PDF for a continuous variable versus probability for a discrete variable. So the key point is here we're dealing with a probability density function for a continuous variable. So the change in the normalization for a continuous variable versus a discrete variable is, for a discrete variable, it's the sum of the probability over all possible discrete values for that variable must sum to 1. For a probability density function for a continuous variable, the normalization becomes the integral of the density over all possible values of the continuous variable must integrate to 1. And the immediate consequence of that is, particularly in cases where the region where the variable has non-zero probability density, if that region is squeezed into a region that's much smaller than 1, then we're going to get density values that are going to go higher than 1 in order for the integral to integrate to 1. Very good question, very important clarification to make. Many people I know get caught on that. Other questions?